Today we are going to discuss about large language models, which is a very hot topic these days. Uh, However, large language models are an evolution of some existing technologies that were there in the deep learning. So we will discuss how uh, the the requirements of the large language models, why it was developed, and why they are so much popular, and what are the paths that were available after the uh, this trend of large language models, and how those things will be affecting our technology field in the future. Right. So let's move into the large first into the language models. Right. So before we discuss about large language models, we have to uh, understand what is a language model. Right. Simply, a language model is just a machine learning model where you are given a set sequence of words, and then you are asked to predict the next word. That is simply what is meant by a language model. Right. So take it like this. Right. So in natural language, I ask a question like Sri Lanka is an island in the Indian, and I am asking the model to predict the next word. The obvious answer is that ocean, right? So Sri Lanka is an island in the Indian Ocean. So when I ask you this question, for you this answer is obvious, right? Uh, if you can train a sequence model, a deep sequence model, or whatever the machine learning model, right? When it comes to language model, so if you can train a machine learning model so that when you are given this string of words, and then you are asked to predict the next word, uh, if you have trained such kind of machine learning model, that is known as a language model, right? So this next token prediction can also be represented in this probability format, where you are given the first word up to the word in the current timestamp, and you are trying to figure out the probability of the next uh, word, right? So this is also a problem with predicting the next token in a sequence model, right? So this is an instance of actually a sequence model prediction. So because this is using the natural language uh, for this process, we call it as a language model, right? So the idea of the language model is that when you understand the language, actually not only the natural language, right, what people use, but when a model has some understanding about everything, right? So everything about knowledge, in general knowledge, language, and everything, it has some sense when the model is asked, model is given the previous set of words as the sequence of words, it can predict the next word. That is what is simply defined by a language model. Right? So this is actually similar to learn how the humans are learning in their early childhood, right? So when you are in the grade 2 or something, so in our time, right? So may not in your case. So in grade 2 exams, you are asked to fill the last word, to like to fill the blanks in the last word, and so on, so that the grades 2 student can, a human being can understand the earlier terms, and he or she should be able to predict the next word. So This is the level of the competency or the intelligence expected from a grade 2 student. So when the grade 2 student has learned some the basic stuff about the world in his or her early childhood, she can predict the next word depending on the earlier set of sequence of earlier sequence of words. So that is what exactly what we are training a language model means. We are training a machine learning model with the earlier set of words, and we are asked to predict the next word like a human being. In the earlier days of machine learning, in order to do the language, in order to achieve the language models, a special form of machine learning model known as hidden Markov models were used. But these days, we are not that much interested in these kind of models because they are uh, lesser, very low in power compared to the existing current day machine learning models. So we are not going to learn about these models, but those were the initial stages of the machine learning where there's a finite set of uh, states in a med in this hidden Markov model, and these probabilities of exit and uh, incoming probabilities are defined for each of the state, and that is how we are trying to uh, that is how these hidden Markov models were generating new words one after the other depending on the probabilities. But for the today's requirements, those hidden Markov models are not sufficient, but we have better models based on deep learning, right? So with the development of deep learning in the deep sequence models, uh, we have LSTMs and GRUs, right? So long short-term memory and the gated recurrent units that have some significant capability to remember the long time history in a sequence, and they can model the sequences in a very efficient way, right? So because of their capabilities, unlike the RNNs, right, these LSTMs and GRUs were able to uh, create some to develop some highly successful language models. Right? So when we were using LSTMs or GRU based language models, each of the word is converted to a vectorized format using the word embeddings, right? So when you are given a sequence of words, each of the word is converted to a vector by replacing that particular word with this relevant word embedding, like something like a word to egg or glow or something. And then these vectors are given to each of the time step of the LSTM or the GR, right? And these models can be trained, right? So once these models are trained, so we have to predict the final the next word, which will also become a vector, but this vector is converted back to its original word by using a softmax classifier at the end. Right? So these LSTMs or GRU based sequence models can be used to develop language models uh, by predicting the next word using a softmax classifier. Right? So by adding more layers or deeper layers into the LSTM layers, or having a lot of data, you can actually make much powerful language models with these LSTMs and GRUs. Actually, you may be thinking, what is the purpose of predicting the last word or the next word, right? Of a sequence of words. Actually, that is a very good question. In the practical world, there's not that much applications, although your model can predict the next one, right? So, because unless it is a problem, other than it's becoming a problem for a grade 2 student to answer in his or her exam, there's nothing much you can uh, do with having a model that can predict the next one, right? You may be, but so you have to. It's not what we really want, right? So actually, what we want with these models, with these machine learning models, are to do some other useful tasks, right? So the idea of using this language model is that these language models can be trained in a sequence model in an unsupervised way, right? If you were trying to do some other NLP related task like text classification or machine translation or question answering, right? You need a set of labeled data, right? For supervised machine learning. If you want to do some classification, you need to have labels, whether it is for example, if it is a sentiment classification, you should need a labeled data set where uh, if the sentiment is positive or negative. If you want to do some summarization, you have to have some text and their summaries as their x and y parameters, right? Like the independent variables and the dependent variable, which is the label, right? So in order to have these label data, it is very expensive because people have to work on them, and you can't get a very large supervised data set. So it is not practical to have very large supervised data set because your economy or your capabilities and the time it takes are limitations when it comes to preparing these large data sets. But when it comes to language models, you don't need any labels, right? So that is the advantage, because when you take a huge corpus or huge text, uh, you can always move your window, right, in the text, right? So as a sequence, through the sequence of the words, and then you can predict the next word in all the time, right? So because of that, you can always uh, get the next word from the text without manually labeling with the help of any human being, right? So when you can scrape the cheap data from the internet, then you can get a huge corpus, and then you can use that corpus to uh, train a language model without any labeling, right? That is the advantage of language model, but not the exact usage of predicting the next word. So why, right? So although you can train this kind of model, if there's no purpose, there's no use of it, right? But if you have learned about transfer learning, right? So you might have learned that if you can learn a specific task in a good way, right, with a certain machine learning model, you can use that same machine learning model for some other task in a higher accuracy with lesser new data, right? So for example, if you want to do some machine translation, right? So that means you want to translate from English to German, but you don't have enough data. But what you can do is uh, you can train a language model with a lot of data in an unsupervised manner, right? So once you have successfully train your model with this task, which is the unsupervised learning task is about training the language model, right? So then you can use this this trained model and transfer learn this knowledge, right? So that means you and train this model again for the machine translation from English to German. So how you do it? Like, for example, there are several ways to do transfer learning, where you can freeze the first all the deeper layers, and you can only unfreeze the last one or two layers, and then you can train one or two last layers with the uh, machine translation dataset, which is a small supervised learning dataset. But because the internal structures of the language is already learned with these language models, which is trained with a lot of data scraped from the internet, now your machine translation would be very accurate, right? So that is the advantage that you can get with transfer learning with the uh, language models, right? So the main idea is that because you don't have enough sufficient label data for supervised learning, first you can train a model with language models, which can be done in the unsupervised learning manner, and then you can transfer learn that knowledge for your uh, useful task, like the machine translation or sentiment classification or whatever it is, with a small supervised labeled dataset. Because you are transfer learning the data, a good large model which is trained for some other purpose, in this case the language model, it has already learned the language or the general knowledge insights in it, right? So you only need uh, a small data set for your task, and this task can be trained in a very accurate way. That is the idea of, that is the advantage of training a machine, training a language model, right? So what are the tasks that you can train it? So you can train it for text classification, like the sentiment classification, right? And natural language translation, like translating from English to Sinhala or Sinhala Tamil or something like that. And text summarization, like you get a news article and you can summarize it into to several sentences, right? So, and you can train it for question answering, where you can ask the questions from the model, and it will answer these questions with its knowledge, right? So this can be extended to maintain a context, and then it would become a chatbot, like the ChatGPT, right? So training with the language model first is known as the pre-training, right? And then you can transfer learn this pre-trained model with your supervised dataset for whatever the task, machine learning NLP task that you want to do, and that is known as the fine tuning the machine learning model, right? So these are some of the examples of fine tuning tasks, right? So for the pre-training, you can use a large amount of data, like petabytes of data, for training this language model, and we can create a very large language model. So that is why why we call it as not as language models but large language models, because uh, the large language models are trained with a lot of text data in an unsupervised manner, right? So that is how the word large language models, or the LLMs, come into our vocabulary, right? So up to now, I have described how the language models, or basically the large language models, can be trained with LSTMs and GRUs, right? So, but this was still not that much popular, because training with LSTMs and GRUs was still not that much efficient. But after the introduction of transformer model, which is an alternative model for uh, training for sequences, like for sequence models, the latest model is the transformer model, where we are not just looking at the sequence of these tokens, but we are focusing more about the attention, and the sequence information is fed into the model using positional encoding, right? And with this new technology of transformers, these large language models were so successful, very, very successful at uh, pre-training and then fine-tuning with other tasks and get very highly accurate results. So that is how the transformer has helped to develop the large language models that we see in the today's world. So, for example, there are several types of large language models. One is known as a decoder-only architecture model, right? So, where the the decoder part of a transformer is trained with in a different way, which is known as a GPT or generative pre-trained transformer. And this decoder only with this decoder only architecture, we could develop a certain large language model with different sizes, generally known as GPT-2, GPT-3, GPT 3.5, and GPT-4. Right. So in ChatGPT, you may find the earlier version of ChatGPT. It was using GPT 3.5, and now GPT-4 Omni. Right. Uh, all these things have raised from the transformer based pre-trained models, right? So in the GPT models, it's on using the decoder part, and you will see how the encoder part is also used for large language models, right? The the cool thing about these large language models is that once you have trained a large language model, not a, uh small language model, when you are increasing the size of uh, the model, that means the number of parameters, right, and the amount of data it is which is used to train this model, something amazing was observed. That is, when we are scaling, that means when we are making the large language model larger and larger, researchers could see that the fine-tuned model with whatever the task, NLP task we want, there were many, many abilities that are emerging, that are getting possible with these larger models that were not observed in smaller models. Right? For example, if you take if you are trying to map the intelligence with humans, our human intelligence can be mapped into many types of tasks like chain of thought, mathematical calculations, understanding jokes, right? And understanding the sentiments. So there are many, many uh, sectors or the tasks that you can train a model for natural language. When the model size is getting increased, they found that more and more complex tasks like understanding jokes and solving mathematical uh, solutions like for like linear algebra the ability to solve these kind of things were also getting possible up to a certain extent, right? When your model is getting larger and larger. So those are known as emerging abilities of large language models. So this paper, there's a paper where they have compared these different types of large language models like Palm, Roper, Chinchilla, GPT-3, and so on. And they were finding when the model scale, the number of flops is the flops is the parameter, the unit used for measuring the model size, right? When it is increased from 10 to the power 18, 10 to the power 20, 22, and 24, and so on, how the accuracy or the BLU score, all of them are benchmarks to measure the performance of the model. And after a certain point, we can see that these abilities are suddenly getting introduced, right? So up to that particular point, that's almost like nothing, right? So after this certain point, it is having some huge increase in this ability uh, with the size, right? So for all these capabilities, they have found that these models were able to do in higher accuracy when they are passing a certain model size. Some of them thinking this can be called as a phase change, like the water is moving to the steam state, right? Like after boiling, or ice is turning into water. That kind of phase change is happening in the large language models when we are increasing the model size uh, at a certain level. It is getting a phase change, and some later papers were saying that this is not really a phase change, but with the number of parameters, that is what we are that's what we are observing. It's something natural which happens in the statistical way, and it is not a phase change. However, what we can say is that when we increase the amount of data that is used to train the model, we can see some impossible capabilities that were not possible with the earlier machine learning models were becoming possible with these large language models, which were not possible with smaller language models, right? So that is something uh, what the human technology has gifted with the large language models, right? So, so what are these newer abilities that are very useful for humans? Like one of them is question answering, right? So in the earlier models, like very primitive uh, natural language generation models like hidden Markov models, there was nothing like question answering, right? So in order to answer a question, the machine learning model should keep the information, the intelligence in its memory to answer a question, right? So it should, like, answering a question is a very higher cognitive uh, capability, right? So not even a small child can answer a question, but you need a certain level of intelligence to a significant amount of intelligence to answer a question, because you should have some understanding and you should be able to generate words in a proper way so that the listener can understand. So it is a very high level cognitive ability is the answering the questions. So chatbot is an extension of question answering systems where it can maintain the context of a conversation and uh, have a conversation with the end user to uh, achieve their goals, or whatever the purpose of the conversational agent or the chatbot, right? So like the chat GPT, right? So That is also a emerging ability that was observed in large language models. And text summarization was also not possible with earlier machine learning models, because in order to summarize some text, you should have some insight, the understanding of the text once you read it, right? So in order to have that understanding or that particular intelligence was only possible after the invention of large language models. So the text summarization was not that accurate until the large language models were invented. The natural language translation was also a very successful task that was possible after the large language models. But even before the large language models, there were some LSTM based language models uh, that were somewhat okay with language translation, like the earlier versions of Google Translator, but they were not that accurate compared to the human translator. But these days, after the transformer-based large language models, now the level of translation capability is even higher than an ordinary ordinary human translator, right? So that is also a result of that is also a capability that came with the large language models. The text classification or sentiment analysis was there, but with large language models, this can be done much more accurate, even better than humans. So let's see what are the things that you have to do in order to train a large language model. Right? So in order to train a large language model, you have to go through three phases. Right? So first one is known as the pre-training. The second one is known as the fine-tuning, and the third one is known as the reinforcement learning with human feedback. Or you will see that there's another way known as the reinforcement learning from AI feedback. Right? There are two ways. The first phase is known as the pre-training. Pre-training means we have to pre-train the LLM in an unsupervised manner for a language model. Right? So this is the largest, the most computation intensive and most expensive task that we have to do in developing a large language model. And the second phase is known as fine-tuning, where you are using a supervised learning dataset for the task that you want to do, and you are transfer learning pre-trained model that you have already trained with unsupervised learning, and now you are supervised learning for your required task, right? Like you are, for example, like you are training for question answering in the case of ChatGPT, right? So in the ChatGPT, they might have used the question answering dataset for answer the questions using this pre-trained LLM. Right? But however, these trained datasets may be having some unwanted content, like some toxic terms, the toxic way of replying to people, right? So some of the content that we are scraping from the internet may contain some unnecessary, toxic, or harmful content that is not suitable for exposing in the production deployment of a LLM. So we have to use the human feedback to refine the conversation with the LLM. In this case, when it is a chatbot, right? So you have to train this LLM for with human feedback. So that is the third phase. So here we are using the reinforcement learning for training for after the fine-tuned model, we get the fine-tuned LLM, which is known as the instruct LLM, because we are using the instructions to fine-tune the large language model. So this instruct LLM is used for with reinforcement learning with human feedback. Actually, we are not for reinforcement learning, we are not engaging with humans, right? So we are using another model for human feedback, and we can smooth the responses that are given by the LLM in the application of a chatbot, right? So let's see what are the things that we do during a pre-training LLM. So which is the most expensive and most critical thing when it comes to a large language models. This is the phase that an ordinary person or an institute can't do by their own, because this needs a lot of resources. Like you need a lot of data, like maybe terabytes or petabytes of data, text that scraped from the internet and from books or articles, and then you have to remove unwanted content and balance the data. Have to do a lot of pre-processing and have a huge data set, and then you have to train this data set with a lot of parameters, like several billions of parameters. It may be like 4 billion to maybe to 500, 700 billion parameters when it comes to the large language model. And then you have to train that model using many number of GPUs or tensor processing units or data processing units, depending on the architecture, which is also very expensive. And you have to run it in a computer where you have a lot of memory, like terabytes of data, uh, terabytes of memory, or many gigabytes of memory are required to train a large language model in its pre-training phase, right? And also you have to train it for several days or weeks or even months for training a pre-trained model. So this is the most expensive uh, learning phase of the LLM. And because this text corpus used for this large language model is huge, most of the tokens that are there in the large language model are omitted from the vocabulary, but only 1% to 3% of tokens from the corpora used in the vocabulary. But still, there would be many hundreds of thousands of tokens that are there in the vocabulary of a large language model, right? And all these things, we can't do it even for a small organization, don't have that much budget. So most of the people who are using the LLMs are downloading or they can reuse an already existing open source pre-trained models, like the GPT models and the Llama models, and there are some other types of encoder-only models like the BART model and so on. Or if you want to have a full transform model, you can use a T5 model. And you can use these models that are available as open source models, and then you can download them, and you can skip this pre-training phase of the LLM because you don't have enough budget or technical capabilities to train it in the pre-training phase, right? And then you can move to the fine-tuning phase. So before we would train, if you wanted to train a large language model in its pre-trained phase, first you have to decide what is the architecture that you are going to use for this pre-training. So, right. So the first, the transformer paper, which is published in 2017, they have introduced an encoder and decoder model where you can see in the middle, right? So, but there are three models that you can train as your pre-trained model. So if you are using both this encoder and decoder parts together, as in the full transformer, this is known as the encoder-decoder model. If you are using only the encoder part, this part, so this is known as an encoder-only model. And if you are using the decoder part, it is known as a decoder-only model. So first you have to decide what is the pre-trained, what is the type of pre-trained model that you are going to train. And if you are using an encoder-only model, you have to use masked language modeling, which is you are randomly masking some of the tokens in the original text, and you are trying to predict the masked token. That is known as the masked language model. So that is used for training the encoder-only models, right? So if you take this sentence, the teacher teaches the students. So you have randomly masked the third token, which is the teacher. Teachers is removed with the masked token, the students. So now the encoder-only LLM is trying to figure out what should be the missing term. And this is known as the denoising, right? So yeah, it is trying to reconstruct the original text that was there in this original data set, right? So in this encoder-only model, it is trying to learn the bidirectional context where it has to learn from this direction and this direction, and it has to understand what should be the context, and then only it would understand what would be the best token that should be there to replace the or fill the mask token to have a meaningful sentence, right? So this is how the encoder-only models are trained. So these encoder models are also known as auto-encoding models because it can automatically, in an unsupervised manner, it can encode the bidirectional context. That means it can learn the bidirectional context in the language. That is why it is known as auto-encoding model, and they are used for mainly for text classification or name entity recognition. So text classification means something like sentiment analysis, word classification, and so on. So the idea of this auto-encoding model is that they can understand what is given in a sequence of words, right? In both ways, right? So it understands the whole sentence as a whole in both directions. That is the idea of encoder-only models. BERT and RoBERTA are some of the open source versions that are available for your purpose, for your development, right? You can download them and then you can use them. If you're using only the decoder part of the transformer, we can have decoder-only models, right? So we are, in this case, you have to train this decoder-only model with decoder-only LLMs using causal language modeling, where you are predicting the last token, like we have learned, right? So what we known as language models in general, or known as full language models. Full language models are also known as causal language models, where you are learning the unidirectional context. You are reading from the beginning to the n in one direction, and then you understand the context in this direction, only this direction, and with that information, then you can predict the missing word, missing token. So the teacher teaches the student, the teacher, and you ask the LLM to fill the next token. So it should be teachers. So after reading these two tokens, this decoder-only model can understand the unidirectional context and fill this empty token with the suitable token. So this is known as predicting the next token. So these models, decoder-only models, are also known as autoregressive models because they are predicting the next token in a sequence. So these kind of decoder-only model or the autoregressive models can be used for text generation. Yeah, you can generate words one by one, like the chat GPT, right? So that you have seen, like the chatbots and text summarization, translation. In all the cases, you have to generate new words one by one. So these autoregressive models are good at it. Right? And also by scaling these models with larger and larger number of parameters, you can achieve emerging abilities like I have mentioned, things like linear algebra, understanding jokes, and psychological capabilities, and different uh, abilities that were not uh, possible with smaller models. Right? So some of the open source available models are for this decoder model are GPT and Blue. GPT model and one of the GPT open source available model is used by the OpenAI to develop its chatbot of ChatGPT. Right? And if you are using both encoder and the decoder parts of the transformer, so that these models are known as encoder and decoder models, where you use the text or some sequence encoding in the encoder, and use this output from the encoded vectors as a key and value parameters to the decoder, and this decoder will decode the input using the input given by the using the vectorized input given by the encoder, and generate some tokens one by one. So this encoder part will still be trained as a in the bidirectional context, and this decoder part will autoregressively create new tokens using the uh, bidirectional context given by the encoder. Right? So in this encoder decoder model, which is also known as sequence to sequence models, what they are doing is they are generating new tokens not only by using in one direction, but using the meaning that is encoded by the encoder. So this accuracy or the capability of this kind of encoder decoder model is much higher compared to a decoder only model. Right? So in this case, we can see this is how the T5 model, which is an open source model that is available. It is what it does is it has several mask tokens, and it is replacing all these mask tokens. It's a separate token known as sentinel token. And the idea of this encoder decoder model is to reconstruct the X token or the sentinel token with the missing tokens, which is teachers, and the teacher teaches the student, teacher teaches the student. This teaches the has to be generated, followed by this sentinel token. That is the idea of using T5 model. So unlike in the encoder model or decoder models, this encoder-decoder models don't have a specific requirement, but it can be used in different ways depending on the application. So it learns the bidirectional context and also it generates the tokens in autoregressive way. So they are used for chatbot summarization, text summarization, and natural language translation with much higher performance because it has an encoder as well, right? So T5 and BART are some of the open source encoder-decoder models that are available. So this is BART, right? So not BERT. BERT is an encoder-only model. BART is an encoder-decoder model. So once you have developed, once you have developed a pre-trained model, like a GPT model, the next step is that you can use it for, then you have to pre-train, you have to fine-tune it with, your data set, which is a labeled data set in a supervised machine learning manner, right? For your own task on top of the pre-trained model. So that is a good thing, as you may think, but however, there's a problem, right? The pre-trained model was trained with a lot of data, right? So maybe terabytes or petabytes of data that are used for training the pre-trained model. But when you are fine-tuning the LLM, what you are doing is you are going to update the whole transformer parameters with your small amount of supervised data, right? Compared to the data that is used for training the pre-trained model, when you are using a fine-tuned model, you are using a very small amount of data for supervised machine learning. But because of that, if you have started to train the already trained parameters with your small amount of data, right, with supervised learning manner, it would forget most of the valuable information that is already learned by the pre-trained model, right? So in the pre-trained model, it has much amount of knowledge that is related to general knowledge and general cognitive capabilities. But once if you have trained this with your supervised learning data set, which has only few amount of data, it would forget most of the important general knowledge that was already learned with the LLM, right? That is known as the catastrophic forgetting. So this forgetting of all the important knowledge that a person should know in general as a human being that was there in the pre-trained model will get removed if you train rigorously with your supervised dataset. That is the main problem when it comes to fine-tuning a large language model. So let's see how we can avoid or mitigate this catastrophic forgetting. Right? So this catastrophic forgetting mainly happens because we are training with a small amount of data for a specific task, right? But right? So when it comes to pre-training, it was trained with a variety of data sets so that it has a variety of data That is why it is capable with general knowledge. In order to avoid specialized for a particular task and forgetting all the other information from the model, what you can do is so this is a one way of fine tuning. So in this way, what you can do is instead of training for a single task, you can train it for several tasks, not only for a single task, but for many tasks that are different from each other, that are independent from each other. So this is a form of multitask learning. Right? Because you are not only training for a single task, but training for many tasks, it would preserve the information that was already there to some extent. Right? So in this case, you are not only training for your specific task that you want to train, but you are training for many tasks, like 50 tasks, 50 separate tasks that we have data sets, right? And then we can reduce this catastrophic forgetting to a certain extent. So for this multitask learning, we can use an already existing technique known as FLAN. In FLAN, we are using many data sets for different tasks for training a model. So when you train a T5 model, T5 transformer based model with FLAN, it is known as a FLAN T5 model. So if you are training a Palm open source model with FLAN, it is known as a FLAN Palm model. So similarly, you can use FLAN technique for multitask learning for different tasks instead of for single task that which we want to train. So that is one way of avoiding or reducing the catastrophic forgetting. But the problem is this is training for multiple tasks, needs a lot of data and needs a lot of time, and it's very expensive compared to training for a single task. Because of that, it is not that much feasible for a small person or organization. Right? So there's another way of avoiding catastrophic forgetting known as parameter efficient fine tune, where we are not going to update all the parameters that are already learned by the pre-trained model, by the pre-training, right? So in the pre-training, we have learned a lot of many billions of parameters, but when we are training for our specific task, we are not going to update all the parameters, but we are only a smaller number of parameters in this phase of fine tuning is known as the PEFT, or the parameter efficient fine tuning. Mainly, there are three ways of parameter efficient fine tuning. So the first way is that we can select the number of parameters in the LLM and do it. So, but this is not an efficient way, because when you select some of the parameters, it would reduce the performance or the accuracy of the model or the quality of the model. So this is not generally done. The second way of PEFT is using reparameterization of the base language model. Base language model means the pre-trained language model. Right? In here, we take the matrix weight matrices and convert them into into two matrices where you are only update. So that means you are basically converted into a lower ranking matrices, and then you can update only some of the parameters after reparameterizing the weight matrices. So this is a form of this involves of technique known as single vector decomposition, as I remember. So here what it, so first you have things, you have to read this paper of LoRA. So this is a form of converting this original weight matrix into two matrix, and you are keeping the vast amount of learning in a matrix which is not getting changed, and you are changing only a smaller number of parameters with your supervised learning dataset used in fine tuning, right? So this is also a good way of uh, fine tuning without updating all the parameters in the transformer or the LLM, uh, which is a good way of not having the effect of catastrophic forgetting, right? And there's another technique known as the third way. It's known as the additive method, where you are not updating anything, or you are not actually converting the weight matrices or anything, but you are keep freezing all the existing weight parameters as it is, and you are adding some other new parameters, and you are training those parameters for your newly added datasets or the supervised learning datasets. So this is known as in this case you can add new layers of neurons, or there's another technique known as soft prompting, where you are adding new word embeddings for the inputs for the embedding space, and for while you are freezing all the existing parameters and embeddings, you are only updating the newly added embeddings for your new dataset, right? So now new embedded vectors are added into the embedding space, trained with the new dataset. That is also a very efficient way of training the or fine tuning the model, which is also a way of avoiding the catastrophic forgetting. And once you have fine tuned your model, you have to come to the third phase of training your LLM, which is the reinforcement learning from human feedback. So as we mentioned earlier, once you have fine-tuned your model, still there may be some problems in your model, because your dataset may contain some toxic content or not that much helpful content, or sometimes there may be some incorrect data. So in order to handle it, especially for the toxic content, where it may create some non-friendly or some harmful content uh, from the as responses. So your LLM should be able to avoid these kind of responses. We are using this reinforcement learning technique, using human feedback to uh, avoid these kind of toxic outcomes for the end user. So in this case, what we are doing is you take the instruct LLM, which is the fine-tuned LLM, and they are trained with reinforcement learning for helpful, honest, and harmless responses. So this can be represented by this 3H, where helpful, honest, and harmless responses are generated from the LLM model. So in this case, we are using the reinforcement learning, mainly the proximal policy optimization, where you are not you are trying to not divert too much away from its original uh, LLM probability distributions in weights, and you are only going to change little by little, and also you are going in this way you are going to measure the uh, probability distributions, weight probability distributions of the new model and the original LLM using the KL divergence, and then you are going to add that term as well and use this term. So I am not going in detail in this lesson. But the idea of this proximal policy optimization is that you are not diverting too much away from the original uh, LLM only because of having harmless and help honest and helpful content. Because uh, when we are if your learning is completely focused about having non-toxic content, it may create some content which is totally non-toxic, but they may not contain the relevant information, so which should not achieve our uh, required goals of the LLM, right? So because of that, we should not move too much away from the original LLM parameters. So this proximal probability optimization algorithm, which is a reinforcement learning algorithm, is used for because of this purpose, right? So in this reinforcement algorithm, we are using a reward model, which is trained by humans to get the reward uh, based on this harmfulness, helpfulness, and the uh, honestness of the model. So this is the diagram of the reinforcement learning for human feedback model. So this is a reinforcement learning agent. This is the environment, and so in this agent, the agent is mainly the instruct LLM, which we have already fine-tuned LLM, right? And this LLM is taking decisions. The decisions that it takes are actually the responses that it is given, or the uh, words or the sequence of words that it is producing as the output, which is the action. So once this action is given to the LLM context, the LLM context is what is given as the output of the LLM. The new state or the new context gets updated, which can also be observed by the LLM in the next phase, in the next step, right? And also this reward model, which is trained by humans, would decide whether this new context is harmful, helpful, and honest. Based on these parameters, it would give some reward like 1 or 0 to this LLM, and this LLM would learn by updating its parameters, and then create and generate new terms or the new responses based on this updated parameters. So this would continue until this reward function is exceeding certain level, right? So something like until most of the responses are not toxic, right? And people have found that this training this reward model with humans was very expensive, because you have to get a lot of people for labeling uh, this LLM. So this reward model is also an LLM, where it can classify whether this context is toxic or not, right? So this reward model training was also very difficult, very expensive, and time consuming when the real humans are involved in it. So this paper, known as the constitutional AI, harmlessness of from the AI feedback, they have developed a new concept known as the constitutional AI, where we don't need any human labelers, but we can write a constitution for the AI, where we are having some laws or guidelines as the constitution for the generative AI. For this generative AI, where it something like it should not be harmful, it should be friendly, it should be helpful, and so on and so forth. We can have some guidelines, and these guidelines, which is known as the constitution, uh, can be applied for the content generated by the LLM, so that the LLM can learn itself to create this reward model itself instead of human intervention. Right? So this is known as reinforcement learning from AI feedback. So instead of humans involving about with the feedback, the AI itself can uh, find whether this generated uh, content is according to the constitution written by the humans. If it is, it would be given the it would be trained as in the positive way, or otherwise this reward model would be trained in a if this generated content is not according to the constitution, it would be trained in a negative way, so that these types of responses are not generated. So when you are training this reward model, first thing is you try to generate harmful content uh, using a technique known as red teaming, where you are writing some prompts to generate some harmful content, and then you are trying to see whether this content is harmful based on the rules given by the constitution. And if it is so, then we ask the model to create uh, a response without this harmfulness, and now then we get the harmless response, and then this harmless response is used as the response for training against the uh, prompts used for creating the harmful questions. The questions that to generate the harmful questions, and for these harmful questions, we are training the model for harmless responses that were generated according to the constitution. So these constitutional generated AI generated feedback is used to train this reward model, where a human is not required, but instead the LLM itself is learning for not creating uh, toxic content according to the using by looking at the constitution again and again. And this is how this reward model, which is also an LLM, get trained, and this reward model can then be used with this instruct LLM in this reinforcement learning technique to train the uh, LLM with reinforcement learning, but not with human feedback, but with AI feedback. Right? So this is an example of constitutional AI, where you can give the uh, instructions like the constitutional rules, like please choose the response that is the most helpful, honest, and harmless. The second term is that choose the response that is less harmful, paying close attention to whether each response encourages illegal, unethical, or immoral activity. choose the response that answers the humans in the most thoughtful, respectful, and cordial manner. Choose the responses that sounds more similar to what a peaceful, ethical, and wise person like Martin Luther King, Jr. or Mahatma Gandhi may say. So you can add these kind of uh, rules in the constitution so that the AI would go through this constitution and find whether this should be, whether its generated content is matching with its with this constitution, or otherwise it would change its generated format, generated response according to the constitution, and then use these responses to train that particular model again, so that it would generate only the, so that it can actually classify the uh, constitutional content and the unconstitutional content in this rewarding mechanism without the involvement of humans. So this is a form of automation that you can use without humans, so it would be less expensive as humans and less time consuming as humans are not involved. So once you have trained large language model, the main problem is that you want to uh, connect your LLM with external systems. So there are new systems where uh, you can connect your LLM with the external applications and the external data sources like databases, internet, and Word documents, and so on, and the user applications where user is having some prompts and so on, and the user questions, and all these things are managed by a orchestration library where the LLM is only interacting with the orchestration library in a specific format, and the orchestration library would do connect with the other external systems. So these systems can get the information from the other resources, external resources, and then you can invoke some APIs in the external systems, like calling a web service or REST service and so on, using this orchestration library, depending on the responses generated by the LLM. So this can make something like an operating system at the end where where the LLM is making decisions, and it can be connected to different ways, like uh, getting information, giving responses, and executing certain functions in a system, like paying payment for a specific food, or purchasing certain uh, furniture for that particular user, behalf of the particular user, and so on, and turn off a certain uh, air conditioner when the user says I am cold, and so on. All those things can be done through this kind of an API where the LLM can execute these external applications through a separate system. So we are not going to discuss in detail how these systems are developed, but these kind of systems are getting evolved in these days, so that you can use your LLM for uh, as a software, so that you can take decisions instead of writing code, but just using the LLM itself. You can give the results from these applications directly into the LLM, and the decision of the LLM can be used in to call certain functions as it is required. In this way, you can replace the programmed software systems with AI systems using large language models in a much more intelligent way. So another problem with LLMs is that although we can fine tune a model, it is very expensive to fine tune a model, because you should need higher number of a certain level of resources like the computation power, memory, and time to train, even for fine tuning LLM. So, and when you're fine tuning LLM, some of the content may not get that much reflected in an LLM. So you should have a certain way of updating the information that is changing in the environment into the, and you have should be able to update the LLM with the new information. So this that is not easy with only with the fine tuning and reinforcement learning with human feedback or AI feedback. So there was a new technique found, but it's not new technique, but there's a workaround that people have found known as the retrieval augmented generation, where you keep the newly changing external information in external sources like vector databases or internet or whatever the file format. And when the user is asking a question, the question is converted into a vector format and it is searched in a, when the question is asked, uh, it is searched in the external information source. Most probably it is a vector database where the query is converted into a vector, and this query vector is searched in the query database. And the closest if it is a, say if it is a cosine distance, the closest vector is selected and its content is appended with the user's query, right? So which contains the information related to that particular query, and that complete query is sent back to the LLM, and the LLM can extract the information from the earlier from the appended content and take the decision and make a better response to the user, to the end user, using this appended content. But there's a limitation because unlike unlike fine tuning the LLM itself, with this retrieval augmented generation, the amount of information that you can add to your query limits only to the context window of the LLM, because you can't add too much information into the context window, but only limited to the total size should be limited to the context window of the LLM. The context window is the uh, maximum number of tokens you can insert into the LLM, right? And it is the same as the generally same as the uh, maximum number of tokens generated by the LLM. So, however, these new RAG systems or the retrieval augmented general systems are getting much more popular these days as they are very highly reliable and they can produce highly accurate responses based on the document externally added documents and other content sources uh, using this external information retrieval related system, which is the RAG. So this is a practical way of using LLMs for uh, dealing with externally changing information. Right? Okay, so this is all for the today's lesson. So if you have any questions, you can ask now.